Hi everyone, so we're going to continue with nonlinear application by using op-amp. For example, here we are using op-amp in a nonlinear application as a comparator circuit. So how do we compare the input? If you see this circuit, there is no connection between both input with the output. Therefore, this is how we're going to compare both input of the op-amp. So for example here, I want to compare Vin with Vref. So Vin is a sine wave. For example, in this case, I put it as 5 sine omega t volt. And then Vref as 2 volt. So here we know that at the peak of the sine wave is positive 5 and minus 5. And our Vref is 2 volt. Okay, so we want to compare these two input and get the output. So firstly, what we need to do is I want to draw another graph. Okay, so for example here we have V out and T. So how do we compare 5 sine omega t and 2 volt? So let's find the intersection between both signal. So we get 1 point over here, 1 point over here, and another point over here. Alright, and then we see where is the input for our circuit. So here in this case, the input is connected to the positive part of the op-amp input, and the Vref is connected to the negative input of the op-amp. Therefore, since Vin is connected to positive part, okay, we compare Vin with Vref, and then we find what is the output, Vout. Okay, so the output will always be either positive 10 volt or minus 10 volt. Why? Because there is no connection between input and output. So what you get is only the supply voltage of your op-amp. Okay, so in this case, the supply voltage for the op-amp is positive 10 and minus 10. Okay, so you will know that your output is a square wave, either 10 volt or minus 10 volt. Okay, and then for this case, since your Vin is at the positive part, okay, if Vin is greater than Vref, your output will be positive 10 volt. Okay. However, if your Vin is less than Vref, your output will be negative 10 volt. Okay, because this is non-inverting op-amp. Okay, therefore here when you see your graph, okay, the signal, the sine wave signal less than 2, you will get minus 10. Okay, so at this point, you will get minus 10. So here at the output part, you can draw line at the negative 10. Okay, and then if Vn is greater than Vref, your output is positive. So here you have one peak over here and also another part over here. So this will be positive. Vout will be positive 10 volt. So at the output part, you know that the output will be positive. Okay, and the value is positive 10. Okay, so when you have these these 4 lines, you just connect to each other. Okay, so this is the output signal. Okay, as simple as that. So here, another example here, number 2. When you have a signal, this is ECG or heart signal. Okay, the heart signal is going to compare with Vref. So the peak of the Vin that is greater than Vref, okay, will get a positive value, positive V or positive 10. But if Vin is less than Vref, the output will be minus 10. Okay, that's why here you can see the peak. There is 1, 2, 3, 4, 5. You have 1, 2, 3, 4, 5. So 5 VCC is positive 10 and minus VE is minus 10. Okay, this can be seems like a digital signal, okay, either 1 or 0. Okay, so same like this as well. Okay, this one you can draw the output. This is the second example like the previous slide. Okay, and then next, if okay, here shows that if the input signal is V minus and V plus, okay, and then we have V out. However, the gain will be still the same. Okay, V plus minus V out multiply with the gain. And then here, the transfer characteristic of the comparator, okay, the output will always be either plus VCC or minus VCC. So, or minus VCC, or maybe the label as minus VEE. Okay, so here you get the maximum value will be the positive value of the VCC, and then the minimum value for your V out will always be equals to minus VCC, right? However, in the practical usage, okay, we cannot really get the V out as same as VCC. Okay, the value will be decreased as there is a voltage usage in the comparator circuit, in the op-amp circuit itself. Okay, therefore, actually the V output that you will get from the comparator circuit will be less than actual VCC value. Okay. However, in our class, we take it as a ideal op-amp where the V output will be VCC plus minus VCC. Okay. Alright, this is another example where you have Vin as a sinusoidal signal here. So Vin is 10 sine omega t volt and Vref is 6 volt. Vmax plus minus is 5 volts. So your voltage supply to the op-amp is positive 15 volt and minus 15 volt. So here we want to compare 10 sine omega t with 6 volt. So here you have 10 sine omega t, and also this is a straight line for 6 volt Vref. Okay, so here you see the input. Okay, the input is connected to positive part of the op-amp. Therefore, if the input is greater than Vref, the output will be positive. Okay, Vin greater than Vref will be positive because Vin is connected to V plus of the op-amp. Okay, therefore the output will be positive or greater, or this is called as non-inverting. Okay, non-inverting op-amp. So here when your Vin greater than Vref, you will get positive VCC or positive Vmax. Or here in this case is 15 volt. Okay, so the greater part, there is two parts over here. Okay, here you will get positive 15 volt. Okay, and then if you have Vin less than Vref, here you will get negative Vmax. Okay, so here 1, 2, 3. So here you will get minus 15 volt V out. Okay, so here the first part is green is negative, so you draw negative. Okay, so negative here, also negative, here also negative. And then the greater part is on the top. Here you have 2 only, here 1 and 2. Okay, so here when you get the result here, you need to continue to draw the voltage. Okay, so just connect your graph. Alright, so that's it. So this is your V out. Alright, let's see another example. Here, the input, okay, the input is connected to the positive VCC. Okay, so what you can do here is you find how much is the voltage at the V minus over here. So here you can use the voltage divider concept to find or to determine how much is your V minus. Okay, so V minus equals to 10K multiply with 12 divide with 10K plus 10K. So here you will get 6 volt. Okay, and therefore you know that your circuit, okay, your circuit here is comparing 6 volt with Vi. Okay, so this is your Vref. You compare with Vin. And your output, okay, your Vout will be equals to either plus 12 volt or minus 12 volt. Okay, so here example for the output, there is an LED over here. Okay, so you know that when when the Vout is positive 12, okay, when your Vout is positive 12, the LED is forward bias, right? So forward bias mean LED is light up or turn on. Okay. However, when the Vout equals to negative 12 volt, the LED is reverse bias. Therefore, it is turned off. Okay. So since your output is changing, Vout is changing either positive 12 volt or minus 12 volt. So therefore your LED will also either turn on or turn off. Okay, you can get like a blinking LED. Alright. However, you need to be careful. Okay, be careful which part of the Vin and Vref is connected. Okay, so here in this case, Vin is connected to positive. That's why at the Vout Vin positive, your Vout will be positive. So if positive, your LED is forward bias and turn on. However, if the Vout is negative, okay, your LED will turn off. Okay, so here is, if you see here, this is about the same circuit. However, the input Vin is connected to the negative part of the op-amp input. Okay, here your V plus is equals to 6 volt. Okay, how you get 6 volt is same like top example. Okay, same like this. You can use a voltage divider. Okay, therefore you will get V plus equals to 6 volt. Here your Vin is at the negative. Okay, therefore if Vin is greater than Vref, okay, Vin is greater than Vref, your Vout will be negative. Okay, negative 12. However, if Vin is positive, okay, Vi is sorry. Okay, Vout will be positive. Okay, therefore here your LED will only turn on when Vout is positive, right? Vout negative 12 volt, your LED is off. Okay, so here you can see the difference between both circuit. Okay, so for this is inverting comparator op amp, when the V out is when V in is at the positive cycle, the V out will be negative and the LED is turned off. However, when V in at the negative cycle, the V out will be positive and LED will turn on. Alright. So this is same what I have explaining. Okay, so let's see the limitation of the comparator. The problem with the comparator is it has a problem with a noise, because in reality the signal is not really smooth. Okay, it might be some noise from the wiring, from the connection, from the supply, so it will get like something like noise in the signal. So actually the signal is not smooth. Okay, so here if we zoom in the signal, you can see there is a okay, here actually there is not only one point. Okay, so if you have VREF, actually in the class we learned that the signal is smooth and the VREF is only the intersection, only what we seen with naked eye is only one cross. Okay, but however actually in reality you can see there is the sine wave. Okay, actually at this point for the sine wave we'll have 1, 2 and 3. Okay, 3 intersection of the signal that cross with VREF. So this is called as a false triggering of the op-amp circuit. Okay, there is one way to overcome this by using a Smith trigger. Okay, so what happens if we have false triggering? Okay, false triggering means it triggered the false signal. Okay, actually your intention is to have a smooth input signal, but however in reality the input signal is not smooth. Okay, so it will create a false triggering of the output signal. So here you can see there is actually you just only want to have one peak over here, but you get two value, right? And also same with this. So it will create a false triggering of the V out. Okay, so let's learn how to do Smith trigger to avoid this kind of false triggering. Alright, so first Smith trigger will have a positive feedback of the comparator. Okay, positive feedback means there is a connection between input and output. Okay, in comparator there is no connection between input and output. So here you have a connection between input and output. So you get here, you can use voltage divider over here at this node, V plus node, okay, to get how much is your V plus value. Okay, in Smith trigger you will learn about two terms, which is VUTP, upper trigger voltage, and there is another one, VLTP, okay, lower trigger voltage. Okay, VLTP and VUTP. Okay, so for this VUTP and VLTP, you can determine it by getting how much is the VREF value, no VREF value, the V plus value. Okay, the V plus value, you will get VUTP and VLTP. So for VUTP, okay, so firstly you take the V out. Okay, you know that your V out will be either positive or negative. V, right? You have here positive or negative voltage supply source to your op-amp. So if you want to get upper trigger voltage, you take a positive VO saturated. VO sat is the positive VCC. In practical, the V out is not as positive VCC here. Ideal is, but practical, since there is a voltage usage by the component inside the op-amp itself, so actually the output is not positive VCC, but it is positive VO set. So here, this one you can refer to the previous slide over here. Okay, this one. Okay. Okay, so if you want to find the VLTP value, you put VO set as a negative value. Okay. A negative output value, V out negative. Okay, so you have negative VCC and negative VO set. But don't get confused, because in this semester we'll just focus on ideal. Okay, we focus on ideal op-amp. So we'll just use either positive VCC or negative VCC. So here you can put as positive VCC for VUTP, and for VLTP you can put it as negative VCC. Alright. Okay, so this is the combination of the output. Okay, so your output will be V out will be either positive or minus VCC, right? Okay, so here positive VO set. Okay, so when you have V in, okay, let's see here where is the V in is connected. Okay, so here V in is connected at the negative part of the op-amp input. Okay, V in is connected to negative of the input. So VREF is at the positive input. So here your VREF is no longer VREF, because VREF here, VREF is the value of voltage at this node. Okay, but now we have V plus over here. V plus here is either VUTP or VLTP. So you have VLTP and VUTP that is connected to the positive input. Okay. So at this point, Okay, for your output, you will compare between VUTP and VIN. Okay, so you will compare these two with VIN. So actually VREF is changed to VLTP and VUTP. So here your V input is connected to a negative part. Okay, negative part over here. Therefore, if V in is greater than VLTP or VUTP, the output will be negative. Okay, negative. And then if V in is less than V in greater than, you have to value, sorry. Because you will compare one by one. Okay, firstly, you compare with VUTP. So if you get V in greater than VUTP, why you compare with VUTP first? Because this is upper value, this is lower value. So if you compare with upper value, it will be as well as greater than lower value, right? So when you compare it with VUTP, if V in is greater, okay, since this VI is connected to negative part, therefore your output will be negative. V out will be negative. And then if you have V in less than VLTP, your V out is positive. Okay, so here let's reinterpret the output signal. Okay, so you have a graph. Okay, V out across V in. So you know here you have either positive or negative, VCC or VOZ. Okay, and then at the input you compare with, okay, your V in you compare with VUTP and VLTP. So VLTP is the bottom value, VLTP, and VUTP is the upper value, VUTP. Okay, firstly you get V out is greater than VUTP, you will get negative value. So here, if V in is greater than VUTP, you will get negative value. So here, VUTP, okay, if V in is greater than VUTP, which is in this side, okay, V in greater than VUTP, you will get negative V out. So you will get negative value over here at the graph. Okay, and then if you have V in less than VLTP, you will get positive. Okay, so here at this part, okay, VI is less than VLTP, you will get positive V out. Okay, positive V out. Okay, so you get these two lines. So what happened in the middle? Okay, so here let's see if VI, okay, if VI is less than VUTP, okay, VI less than VUTP, you will get change color, easy for you to see. Okay, if your input is less than VUTP, you will get same like okay, so if you get it less than VUTP, you will get positive value. Okay, if you get it greater than this one, VI, you get greater than VLTP. Okay, in between of the VLTP and UTP, you can get both. Okay, you can get positive V out or minus V out. Okay, you can get both value. So you can draw. Okay, so here, you know, up to firstly, V in is less than VLTP, you get positive. Okay, so you get a positive value. However, if how to create the line, okay, in between VLTP and VUTP, you can get both value, negative or positive, and then greater than VUTP, you will get negative. Okay, so here, if your V in is equals to VLTP, so how is your signal? Okay, if you get VITP equals to VLTP, of course you will get VLTP, right? And then if you have V in equals to VUTP, of course you will have V out equals to VLTP, isn't it? So here you can get two value, either VLTP or VUTP value for your V out. Okay. So here the output signal looks like this, because you will have one condition, two condition, three condition, and also four condition. Okay, so you have 1, 2, 3, okay, and 4. Okay, but here you see in the graph over here, there is an arrow. Okay, so how to draw this arrow? Okay, I padam jap. Okay, so here let's see if your VI is going to be less than VLTP. Okay, VI is less than VUTP. The output will be to the less than VLTP, which is goes to the positive VO set. That's why the arrow is pointing to this direction. And then if you have VI greater than Vout, okay, the output will always be VUTP negative. If you have VI greater than VUTP, it will always be negative. Therefore, the arrow is pointing to more greater VI value. And then if you have at this point, okay, at this point VI equals to VUTP, you will get a negative Vout because the VI will be more less than VUTP. Okay, so the arrow will goes to the VLTP, and then from the VLTP value, it cannot go down because the output will tend to go to the positive part of your Vout. That's why the arrow is pointing upward. And then for this part, the arrow is when the VI is greater than VLTP. Okay, from here, okay, here at this situation, VI equals to VLTP, right? And then if VI became greater, it will goes to this direction. However, the value will be still maintained at positive VO set. And then it will goes down when it reach to VUTP value. Okay, so that's it. So there is a property of the Smith trigger. Okay, it will have a hysteresis, or the behavior that is differently act when the input keep on increasing. Okay, from the way it behaves when the input is decreasing. So how much is the hysteresis voltage value can be found by using a voltage divider method. This is another example by using Smith trigger. So here VI is 10 sine omega t, and Vref here is 6 volt. So what you need to do is to find how much is your V positive. Okay, so V positive will be VUTP and VLTP, because your Vout will be positive 10 or minus 10. Okay, just put a voltage divider equation into the V plus value and you will get VUTP and VLTP. So in this circuit, you will get 8.67 volt and minus 4.67 volt. Okay, so this is your V in 10 sine omega t. Your VUTP and VLTP is this one, VUTP and VLTP. So how to draw the Vout over T signal? Okay, firstly you draw the VUTP and VLTP value on your V in graph. Okay, so here from your VOVI graph, Okay, you can see this is VLTP. Okay, so if VI greater than VUTP, okay, this part, your output is negative 10. Okay, so VI greater than this point, your output is negative 10 volt. Okay, so here is where VI greater than VUTP. So at this point, you will get Vout equals to negative 10. Okay, so you draw on your V output voltage. Okay. And then if your Vin is greater than VLTP, okay, Vin is greater than VLTP, what you get is Vin greater than VLTP. Okay. Okay, Vin greater than VLTP means the signal is pointing to this direction. Okay, this one you will get Vout positive 10 volt. So find on the graph Vi greater than VLTP. So here is VLTP. Okay. Okay, so here, okay, your Vin is greater than minus 4.67, and also at this part, okay, greater than, right, because the signal is going like this. So here, at this orange color, you get positive. Okay, this one also positive. And then from, if your Vin is at the middle over here, okay, Vin in less than VUTP but greater than VLTP for this one. Okay, first one is VI less than VUTP greater than, right? Greater than VLTP. So this one for this case and also this case. Okay, here Vin less than VUTP but greater than VLTP. So here Vi less than VUTP, okay, less than mean over here, right? And then greater than VLTP, so at the middle of the graph. So how much is your value? So here what you can do is, okay, draw the, okay, so here the signal is from the high value and then it reach VUTP and then it goes down, right? So means the signal is from Vi, it goes to VUTP and then it goes to VLTP. So it goes to this direction. Okay, this directions mean it follow this value. Okay, so here is this value is negative 10. So at this part you will get Vout is equals to negative 10 volt. Okay, that's why here you get negative. Then this one also you get negative. Okay, so here another one here, and this one. So here the V in is less than VLTP. Okay, so here V in less than VLTP. So means the arrow is from VLTP and then it goes down. Right, it goes down to this side. So here, okay, if it goes to the left, it follow this arrow on the top. So this one you get positive 10 volt. So here your V out is positive 10 volt. So you draw the output positive 10, and also here you get positive 10. Okay, so that's it. And then you can just connect your signal. Alright. Okay. Okay, so this is another example. Okay, so this one, Vref is changing from 6 volt to 0 volt. Okay, so you can try and get the output V out over T. Okay, you can see there is a difference. When you have different Vref, you will get different VUTP and VLTP. So changes in your VLTP and VUTP value will create a different output. Okay. So that's it for nonlinear op amp by using Smith trigger.